There are two equations that we are going to use in this lesson, and here they are. The mirror equation, 1 over p plus 1 over q equals 1 over f, and the magnification equation, m is equal to h prime over h, which is also equal to opposite q over p. Down below we see the definitions for the variables that are in these equations and their sign conventions. I explained those a little bit in an earlier lesson, so I won't do so now. Possibly the most important thing to remember when you're using these equations is if you have a concave mirror, the focal length is positive. If you have a convex mirror, the focal length is negative. In a previous lesson I also went through the mnemonic for remembering that the object distance is symbolized by a lowercase p and the image distance symbolized by a lowercase q. If you take the b in object and you flip it upside down, it turns into a p. If you take the g in image and you turn the little crook the other way, it turns into a q. That's one way to remember that the object distance in these lessons will always be symbolized by a p and the image distance symbolized by a q. It also turns out that inverted images are always real images. Upright images are always virtual. In other words, inverted and real, IR, go together. Upright and virtual, UV, go together. And if you remember that IR is kind of an abbreviation for infrared and UV is an abbreviation for ultraviolet, that might help you remember that inverted images are always real images and upright images are always virtual. So let's do a problem with a convex mirror. First of all, anytime we have a convex mirror, we know without even doing any calculations that we're going to get a smaller upright virtual image. If our numbers don't bear that out, we've clearly done something wrong. Convex mirrors have negative radii of curvature and they also have negative focal lengths. So the focal length here is going to be negative 32. It's very important that we use negative 32 in our calculations whenever we get to using the equations. The height is 24 centimeters. The object is 30 centimeters from the mirror, so p is 30. There's our mirror equation. We want to solve it for q, which is the image distance. So we're going to subtract 1 over p from both sides. Then we're going to take the reciprocal of both sides to give us an expression that is equivalent to this. And I'm okay with fractions in the denominator, so I'm not going to simplify it further. Notice here that we've put negative 32 in for the focal length. Sure enough, the negative image distance tells us that we have a virtual image. And virtual images are always upright. So of our three conditions, smaller, upright, virtual, two of them we've satisfied and we've shown that we're correct using calculations. If we now calculate the magnification, it's equal to opposite q over p. Again, be careful because we're going to end up with a double negative here, which is going to give us a positive numerator. That magnification being less than 1 tells us that we have a smaller image than we do an object. And virtual images are always on left. If you want to know the actual height of the image, we can calculate it here as 12.4 centimeters. If we take that same problem and we draw a ray diagram for it, we will see that we definitely get a smaller upright virtual image. Final thoughts on convex mirror calculations. You must know the sign conventions for focal length in order to solve mirror problems. Convex mirrors have a negative focal length and a negative radius of curvature. One way to remember that is if someone vexes you, that's a very negative emotion. So convex mirrors have a negative focal length. In using the mirror equation, be sure to solve for variables carefully. Under no circumstance should you begin by writing P plus Q equals F. That is wrong. For convex mirrors, there is only one essential answer. The image will be SUV, smaller, upright, virtual. Period. End of story. Best of luck.